Super professional fade out. All right. How was lunch? Good? Yeah? Spicy? Yeah. Is anybody keeping up to date on Silicon Valley, that show, on HBO? Yeah. So been some recent stuff about image recognition. I'm not going to do anything related to that, but, hot dog, not hot dog. Anybody familiar with that? I just wanted to get that joke out of the way because that's where everybody goes right now when they think about machine learning. All right, so we got about 30 minutes. We got a very hot mic. Sure. We'll just run the risk. So let's get into this. So this is going to be about deploying image recognition on Kubernetes with TensorFlow. Is anybody here doing anything with machine learning right now? Nobody. Is anybody interested in doing anything with machine learning in the near future? This is awesome. You're in the right place. Tell your friends. They should have been here too. So let's go over a few things. One thing is that I'm a person. I work at Google. I do architecture advocacy. I generally teach people about good architectural practices, do advisory work, that sort of thing. I also do a bunch of other stuff. The things that I'm interested in the most these days are mostly around rock climbing. I don't have a lot of time here in DC, but if you know of a good bouldering gym, I want that advice, and you can hit me up on Twitter at Casey West. Pretty easy to find, but I would love, if you know of a good gym, for you to tell me for the next time I'm in town. I mentioned that I'm this architecture advocate at Google. I am not a data scientist, so this talk is not so much about data science. That's not what I do. I'm also not an expert at machine learning. But what I wanted to prove to myself, and what I hope that I can show you as well, is that it is possible to support data scientists and people who are experts at machine learning and deploy these technologies and manage them at a reasonable level of scale. So I want to show you what that would look like. So that's what I want to do today. But in order to do that, we do have to generally walk through some machine learning. And I wanted to provide a reasonable practical example. So I'd like to actually show you what it would look like to interact with a trained model. So, although I am not those things, I know enough to be dangerous, and in roughly 28 minutes, you will also know enough to be dangerous, and hopefully this can help us on this journey to take advantage of more machine learning capabilities in our organization. So let's get dangerous. I don't know if this rings for anybody else, but Darkwing Duck is the shit, so, Yeah, okay, right on. Does that come through on these slides? I can't even see the screens. I just have to trust. Okay. Right on, right on. Okay, so we have a project plan. We have a thing we want to get done today. We only have a few minutes to do it. All right, phase 0, because we always start with 0 because we're nerdy. We have to understand something about machine learning. Then we need to create a TensorFlow serving model. TensorFlow serving is a specific project that helps us deploy and make available machine learning models more easily. It's part of the open source community projects that the TensorFlow community has created. Then we want to take advantage of that. If we can serve machine learning models and make them accessible, then we also want to write some app that would interact with that, right? So that's the thing that we would want to do. And then we want to deploy this thing, and I see no reason why we wouldn't deploy it onto Kubernetes. And I'm here rocking at this Red Hat thing, so I think it's worthwhile to mention that what I show you today would run pretty well on OpenShift or raw Kubernetes. I'm going to show you raw Kubernetes because I'm a big fan of open source, but OpenShift is just sitting right on top of that and working just as well. So you got all that going for you if you want to use any of those technologies. So let's understand some machine learning basics. Shrug, this is hard. So I mentioned that I'm not a machine learning expert, so I'm going to give you a surface level understanding of roughly what you have to do to implement some kind of machine learning thing. So we have to train a model. And in order to train a model, there are a few things we need. The first thing is data. We need historical or past information. We need a corpus to work from. And this corpus is how we train a model, how we teach a machine learning algorithm to recognize things in new data, right? So we have to start with something. We have to have stuff already. So if we're going to use image recognition, a good example of things that we should have already are a whole bunch of images, right? And maybe some general understanding about what those images are, right? Those are things that we need. We also need time, because in order to train a model efficiently, you have to teach it. And in order to teach it, just like a human being, we have to have exposure to as much information as possible in order to train our model well. So the more time and the more exposure we have, the better understanding we have about the world around us. This is how our brains work, and that's why neural networks that are baked into machine learning models operate in a similar fashion. You train them by exposing them to more and more information and getting them to learn about that information. And of course, we need some algorithm. So that's the procedure. So these are the three building blocks of doing any sort of machine learning. You start with a corpus of information. You have time to run that information against some algorithm. That algorithm and the way that we configure that algorithm is the procedure that we need in order to move forward. So when it comes to data, as I said, you need some sort of historical data or available data. So there are a bunch of machine learning models out there in existence already. We're going to use a pre-trained model for this talk, actually. I'm going to show you image recognition using a pre-trained model on an academic data set of images. It's called ImageNet. And that corpus is often used for academic research around machine learning, especially with vision and image recognition. But another good example would be the fact that Google has machine learning image recognition APIs, for instance. I work for them, so I know we have these things. And we train our model against nearly every image in existence and a good understanding of what those images are, at least anything that we can find on the internet. So that's a trained model against a huge corpus. So the more data you have, generally, the more effective your model will be at finding what you're trying to look for. Then of course, we need time. And these are about making iterations. So in addition to just running data against a procedure by exposing a procedure to more and more information so that it can be trained better, you can also adjust those procedures and rerun the information. And of course, you get new data or new information, for instance, images, all the time. So you can run that against your model and train or enhance the training of your model over time as well. So that's why time is a significant factor. The more time you have to train your model, the better prepared it will be when it comes into contact with some new piece of information. And of course, as I mentioned, we need the procedure, which is how we discover data and prepare it for procedures. It's also the algorithm we're going to use. There are some common techniques in math that I am not an expert in, as I've already stated. And then there's ways to configure those algorithms to tweak them so that they behave in a certain way. So we take these steps. So we have to get some data set, and we probably already all have a data set. Now, as I said, we're going to use image recognition for this example, but we might use a bunch of data or a bunch of, text in order to do sentiment analysis or to try and extract keywords or understand the composition of natural language so that we can try to infer insights from information that we have. That's another common example. We could also look through video and do the cool thing in the movies that my talk title suggests, where we can find faces in a video and then enhance, like zoom in, which of course the enhance thing is a total lie, right? We all know that by now. Hopefully people in this room especially know that, I hope. But it is totally possible these days to find faces or other identifiable marks in video, for instance, and you can do that by already having a data set that you can train against an algorithm to find things like that. Then when we have this data, we have to split it into two groups. There are two basic schools of thought on training a model, but in order to train a model, much like software development process that we do today, you have to build some algorithm, run your data against it, and then you have to validate the results of that outcome. So we like to call that testing in software delivery right now. If we build software, we tend to try to test software, I hope, whether it's manual or not. But in machine learning, we do the same thing. So you have an available corpus of information, and you train the model against a significant portion of that information, and you use a remainder in order to validate the training. So you take a collection, say 10% of your images, and you set them aside. You run training against the images that you have, and then you validate that the images that are remaining get classified the way you would expect. So the images that you have remaining as an image of a spider, your classifier should say it's a spider if that's the sort of thing you're looking for. If it has an image of a public figure, it should be able to say that is our president or whomever else it might be, right? You should be able to identify these things and validate that the training that you did actually comes up with the outcomes you expect. So very similar to software. Now, as I said, there are two models. One is a single pass, where we take the bulk of our data set and we use that to train the model, and then we take a smaller subset in order to validate. The other one is where we do a multi-pass and we do a composite of the training results from multiple passes. So we break a data set into multiple sections, we train every section, and then we cross-validate them across the trainings. So we determine whether or not we're getting similar results by validating separate data sets against one another, or the results of training separate data sets against one another. That can yield more iterations and more nuance in your training models, and both options are valid and used pretty commonly today. So we take this data, we split it up, we train the algorithm, and then we test the algorithm, and then of course we ship it to production because everything is great. Because that's just how we do. We talk a lot today about like just shipping things to production, everything will be fine. So this is the basic process for machine learning. Now, if you want to know more, there's a gentleman by the name of Suraj Raval who uploaded a video using Python and TensorFlow directly. So this doesn't use the TensorFlow serving with network APIs, but he does get into a little bit more of the maths than I do in the first 5 minutes and shows a little bit of code as well. I'm going in a different direction, which is how can we deploy and manage these things. But if you want to know more about the machine learning, this is a fine place to start. This video is pretty cool. I will, by the way, tweet out a link to these slides that get published after this talk. And also this talk, I believe, is being recorded. So you'll be able to get things like links pretty easily. So we're going to use a pre-trained model, as I mentioned before. There's an image recognition model called Inception. This chart clearly explains everything. So this chart is actually on the GitHub repo homepage for this particular model. I actually don't understand what it says at all, but that made me laugh so much when I looked at it that I just decided to throw it in here. So if it explains everything to you, that is fantastic. Good for you. But Inception is an image recognition procedure where they've taken that academic collection of images that I mentioned before called ImageNet, and they've run it against this algorithm. And then this is a third published version, so that's why it's V3. They called it Inception just because you have to name things, right? So they named this particular procedure Inception. So we have a pre-trained model that we can actually serve up and then classify images against, which is kind of nice for someone who's not an expert at machine learning, and it's a nice place to start. As I mentioned before, the capabilities of your model to classify images accurately has nearly everything to do with the data set that you start with. So the image, or the academic data set called ImageNet that Inception begins with is good for academic research. It's a nice place to start. We'll actually see how it does live. But if you have a particular use case, then you could train the algorithm against a different data set and come up with different outcomes. And I think that's important for us to know. If you wanted to take this to the next level in terms of building a machine learning model that is trained to your specific needs, that's totally possible. And you can even start with the algorithm that's baked into Inception. You can go on GitHub and start playing with it. So for instance, I thought about a thing that I would love to do someday that I think would be fun to do in a talk, which would be to take this algorithm, but start with an image collection that are all of the scraped images that tag my friends on Facebook. So collect all of my friends off of Facebook and then run it through the algorithm so that I get an algorithm that is highly trained to find my friends. And then take pictures and determine whether or not, like live, if there's somebody that happens to be my friend on Facebook, it should be able to find that person and be like, that's Ming. Ming over there is a friend of mine. I'm not sure if we're friends on Facebook, but we could be. Okay, we could be. We'll talk later. Yeah. Come to the happy hour. Okay. So it could find Ming, and then if I took a picture of a stranger, it would be like, that's not my friend. Now, I know that's like hot dog, not hot dog. But, you know, it's a little more nuanced. In any case, that is totally possible. It's a thing you could do. But what we want to do is we want to take this model. If we have a machine learning model that has been trained, and thankfully there are pre-trained models out there to do things like image recognition or handwriting recognition or sentiment analysis, then we can serve it up. And I'm going to use this open source project that's part of the TensorFlow community called TensorFlow Serving to do that. So TensorFlow Serving does a few things. As a piece of software, it provides a continuous training pipeline. So if we think about continuous delivery in our software, this is very analogous. The idea that you can constantly be refining the training of your algorithm by providing it new data as you get new data. So this TensorFlow Serving project provides the framework for making that possible, making it really easy. It also provides an interface over a particular API protocol called gRPC. Is anyone here familiar with gRPC or proto buffers, or have you ever heard of that term? A couple of folks, or one folk. One individual has. So I'm not a gRPC expert either, but gRPC provides an interface for TCP connections that's highly efficient in terms of transport and also has some structure to it. So you send a payload or a message that's in a particular structure. And gRPC is analogous to like RESTful APIs, but it's often more efficient, especially for chatty applications or applications that require a lot of back and forth. So internally inside of Google's architecture, for instance, gRPC is used nearly everywhere for services to communicate with one another, as opposed to stateless RESTful, HTTP APIs. So this is just a different type of interface. It's also production ready, so it's used in production fairly frequently. Another key aspect of TensorFlow serving, which isn't on this slide, is that it allows us to serve multiple trained models and multiple versions of those models. So we can actually use it for interaction with multiple models, multiple machine learning versions of those models as well. So you can serve up your image recognition as well as your sentiment analysis and multiple versions of those things, so you can test them and iterate over your machine learning models just the same way that you would with your own code and capabilities in your software. So that's pretty neat. So let's start by containerizing these pre-trained models before they get away. This is, I don't know, I felt very Pokemon-like when I said this. So, we don't want anything to get away, so we'll just throw it in a container. I feel like that's what Pokemon is. Okay. So I'm going to start with a Docker machine in order to build a Docker image. So I want to build a Docker image that encapsulates TensorFlow serving and my model, my machine learning model, so that I can serve it up, so that I've got this immutable artifact that I can ship around, and I can also scale up, and I can scale out as well. So in order to do that, I need to build a Docker image, and the instructions and the way that we're going to do that with TensorFlow serving are actually a little bit of a, I would say it's a little bit of a pain in the neck in terms of it's not like a one-step 15-minute process. It takes a little bit of effort. One of the things I want to point out here is I'm going to spin this up on Google Cloud because that's what I have available to make machines easily. And the machine type of N1 standard 4 is a 4-core or a 4-CPU machine. And the typical thing that you get when you spin up a Docker machine is a micro machine. It's a really small machine. But in order to build the machine learning model and integrate it into TensorFlow serving, we actually need a little more horsepower. So that's the thing I wanted to point out there, is you need a bit of a beefier machine, or it may never finish, or it's going to take an incredibly long time. I had to learn that the hard way by trying over and over again on a micro machine with 600 megs of memory and, I don't know, like half a CPU or something. But we're going to get this machine up and running. And then what we need to do locally is that we want to run a developer container. So the developer container allows us to import our model and compile this stuff. So we're going to start by cloning the serving repo, and then we'll run Docker build. And thankfully, the serving repo provides this developer environment for us as a Docker file that we can use to build and then run a container. And inside of that container, we'll actually organize the environment. So this is a place where I wish this were more streamlined, and unfortunately, it's not yet. So this thing is still requires a little bit of work. So that's what we're doing here. Has anyone here built a Docker container before, or run a Docker container? Okay, so we've got some experience in the room, but maybe not a lot. As you can see, there are only a couple of commands to run. They're pretty easy to at least cut and paste, which is kind of nice. So then we want to, inside of the developer container, we want to build our environment. So inside of our developer container, we're also going to clone this repo, and then we're going to configure it. And this is the part where this could be fully automated, but the configure process is interactive right now. If you've ever run configure to build a piece of software, especially as something that's sort of low level, you know that sometimes it asks a lot of questions, and you also know that you can often provide command line arguments. Some of them might be like just assume the defaults and build, or you can specify specific arguments. Unfortunately, this configure environment doesn't offer that easily yet. So this is like an area where one of us, maybe me, has to submit a pull request to make this better. So once we configure this, then we can build. And the build tool that we're going to use is Bazel. So Bazel is used by the TensorFlow community, and it's another thing that's used internally at Google a lot. So it's another piece of open source software that's just a build tool, kind of like make. So we're going to build TensorFlow serving, and that's the command to do it, even with the 3 dots. But that's how we do it there. And this builds the TensorFlow serving environment inside of this development container. The next thing that we need is we need a model. I mentioned that I'm going to use this pre-trained model. The URL for Inception version 3, which is a tarball that we download, is really long, so I made a short URL, which happens to work. But we want to download this thing, and then once we do that, we can run Inception saved model. And at this point, we can provide the checkpoint directory. This is where we've made an export of our version of our trained model. So this happens to be Inception v3. And then we want to output it into Inception export. So this is how we get a saved model into a form that TensorFlow serving can serve up for us. So at this point, we've done everything we need to do in our build container. And now we need to commit this thing. Again, this is not as streamlined in CI/CD as I would like it to be yet. But I wanted to show you the truth. I'm not going to sugarcoat it. It takes a little bit of work. But at this point, outside of our container, we want to commit this state. So at this point, we have a built TensorFlow serving environment. We also have a machine learning model that's been imported in a way that we can serve. And we can commit it and tag it. And when we tag it, we want to upload it into some sort of Docker registry. And in this case, I'm going to use the one that's provided by GCP internally. You could use Docker Hub. You could use your own. It doesn't matter. But as you can see, if you've done anything with Docker before, I'm just going to tag it with the location, and then I'm going to push it into that environment. In this case, I'll use the gcloud push command, but you could also use the direct Docker push command. So at this point, I've got a built TensorFlow serving backend, right? It speaks gRPC. It understands machine learning through the Inception v3 algorithm and the trained model, and we have that part in place. So at this point, what we want to do is deploy this thing. And in order to do that, I want to deploy into Kubernetes. That's the point of the talk. So I'm going to build a cluster or start a cluster up on GCP. But we should just do this part live. So what I want to do is start a Kubernetes cluster. Let's see where we're at on time. We're doing OK. So to start this Kubernetes cluster, I'm just going to do gcloud container clusters. Create. And we'll say that it has 5 nodes. So this will spin up a Kubernetes cluster for us. Cool. And while that's going on, I actually want to go over into some code. So we have this backend service. It's with a pre-trained model. But I also want to write some software that interacts with it. So what I want to do is, because this thing speaks gRPC, and that's actually kind of challenging, is I'm going to put a small RESTful API on top of it. So I'm going to build a little microservice that speaks a language that the rest of my architecture understands. And I'm going to use Node.js to do that, actually. So let's start with package.json. How many people here feel like after lunch they can read some JavaScript today? OK, cool. And if you don't, as I said, I have Red Bulls in the front. You're welcome to grab some. But I wanted to use JavaScript. Typically, most integrations with TensorFlow are done with Python. Python is sort of a de facto for doing machine learning and data science as a language. It has a lot of libraries that make it incredibly easy. Java has a lot to work with as well, of course. The Spring environment is something that I'm a little familiar with. They've got a bunch of stuff. But JavaScript is something that a lot of day-to-day engineers are using to build microservices as well. So I thought it would be interesting to try something different. One thing I want to point out here is I'm using a library called TensorFlow Serving Node Client. So this is a node client that speaks gRPC and understands how to talk to the Inception v3 image recognition environment in particular. And I'm also using a specific branch which integrates a pull request that I've provided on GitHub. So I'm just pointing this out here. This branch, all it does is make the library compatible with version 1.0 of TensorFlow and TensorFlow Serving, which came out recently. So there's a slight interface incompatibility, but with the GA of 1.0, we had to do a little bit of extra work here. So let's go ahead and go through this, this library. And what I'm going to do, by the way, while I'm doing that is let's just watch in the background as this cluster gets created, make sure that we know when that's done. So to start, I'm trying to build a 12-factor application that will run really well whenever it's containerized. So there are a few things that I have to do. One of them is I'm going to get my port that I'm supposed to bind to off of the environment. So when I want to run a web server, I need to bind it to some port. I can't hard code port 80 or 443 or anything like that. So I'll just get that from the environment. I also want to get information about how to connect to the TensorFlow backend off of the environment. So when we deploy this thing to Kubernetes, the backend will be exposed as a service. And when it's exposed as a service, that provides us some environment variables for service discovery. So we can get information about what host and port we should listen to. And in this case, this will actually map to a load balancer, which is in front of a number of backend servers, or backend instances, I'll say. And then I'm going to use Express to just build a basic JSON API endpoint. So just to walk through this here, here's our client, by the way, where we're going to connect using the host and port that we got off of the environment. And so when we go to the root URL, we're going to get a URL for an image on the internet. And the URL for this image will be the image that we want to classify. We want to run it through our machine learning algorithm. So I'm going to start by just providing a URL to some image on the internet. And then I'm going to make a request for that image. So I'm requesting this URL, and with this particular library that I'm using to make requests, I also have to specify a null encoding so we get the binary data back. So we can actually get the binary body of the image, which is, of course, some JPEG or whatever. So in order to get that image, it'll be in image client body here. Here we go. So we've got a cluster running. By the way, now that this cluster is running, before we move on, I'm just going to go ahead and use kubectl to deploy my applications. So I'm just going to do create, and I've got a Kubernetes environment here. So we're just going to get that spun up. And then we're just going to watch the state of services and pods so that we can watch this thing spin up too. So we should be able to see how this deployment progresses as well. But while we're doing that, we'll get the image body, and then we want to run it against TensorFlow's image recognition model that we have from TensorFlow serving. So against the client, we will run predict. We'll provide the image body as a binary piece of data. And we'll go ahead and send, once we get back a classification, we will send a response. So this is the JSON we're going to get back from our API. We'll provide the source image URL, and we'll provide the classifications that we get. Okay, so this is a pretty basic interaction. And just so that you are aware, inside of the library for TensorFlow serving, let's just peek under the hood a little bit. We can see these particular lines of code, which are the important bits here, where we're going to send a protobuf, which is basically that structured message over gRPC to TensorFlow. And this is the type of structured message we're going to send. We have to send the type of model we're trying to run against. Its name is Inception. It's called predict images in terms of its signature name. And you can see that for inputs, we're going to provide this string, which is actually the image itself. We have to specify the dimensions of our inputs. And in this case, for an image, it's just the length of that image. And this is how we send something over to TensorFlow. And we'll see what we get back once this thing is up and running. So we're still creating containers. We don't have external load balancers in front of our services with external IPs just yet, but they'll get there. So the next thing that we need to see is we need to see our Kubernetes configuration. Has anybody tried to do a Kubernetes deployment before? Are anyone there? Or an OpenShift deployment? I guess that would be pretty similar. So we can just look through this very quickly. Let's start with the backend. So we want to deploy the backend, and we have to start with the deployment. We're going to run 3 instances of the backend. Okay, we've given it this label, Inception Service. And you can see that for a specification for what to run, we're going to run an Inception container. We're going to get it from our repository here. And then the command to run is that we're going to run the TensorFlow model server. That's the application we want to run. We're going to run it on port 9000. And of course, we have this model name, and we have the place where we exported our pre-trained model, or our trained model. And that's the model that we're serving up for this particular instance. And then you can see that we're going to expose this as port 9000. By the way, anyone who's astute here would see that I hard-coded port 9000 in my arguments, and I probably should have made that an environment variable, and I totally agree. So the next thing that we want to do here is we want to expose this back-end deployment as a service. By exposing it as a service, we'll expose it through a load balancer, and that'll make it available or accessible to other applications in our environment. in our architecture. And so what we want to do is just go ahead and expose it on port 9000. As I said, we're going to expose it through a load balancer, which integrates with your provider. So on AWS, this would be an ELB that would get spun up, right? It would get an external IP or an internal IP, depending on how you configure it. And then, of course, you specify the port, and then you can access it. In this case, it's going to be a Google global load balancer because I'm running it on GCP. And then as far as the client is concerned, we're going to do something very similar. We'll run 3 instances of the backend service. And our container has already been built from that JavaScript that we saw, which is this inception client. We'll expose it over port 8080. And then in order to make it available as a service, again, we'll put it behind a load balancer, which is bound to port 8080, and will load balance our requests to the front end. So we've got load balancing in place. We've got backend instances. We've got them scaled up to some level of high availability. And that's not bad. So at this point, we're still creating the containers. It's pulling these things down and getting them up and running. Once that's up and running and we have an external IP, we'll be good to go. I recognize that it is 1:30 and we have a 10-minute break. I'm going to try and get this thing to run. Demo gods be with me. We'll get some instances up and running, and we'll be able to do some machine learning. So one thing for you to know is that I've got some images that I've uploaded already to Google Cloud Storage, and I've made them publicly available here. So for instance, I've got a government building. That might be the most relevant thing here. I've also got an image of Washington, D.C. So here's Washington, D.C. I think that's a pretty common view of Washington, D.C., the metro. That was funny to me. No? Okay. And this is my government building, a building that's getting a lot of attention today. I also have a couple of others just in case we have the opportunity in terms of time. The kittens and puppies are always popular. And then there's an image of me as well, which is terrifying for me. But so if we get around to it, we can do kittens, we can do puppies, and we can do me. But let's stick to Washington if we can get away with it. Okay, so we're still waiting on an external IP, and we're still waiting on some containers to spin up. So as soon as those things happen, let me just open up a new command here. We're going to curl, and what we want to do is we want to connect to the client service, and we should be able to run a RESTful API call. The only thing that I need in order to get to the next level here is I need an external IP to be provided for me once the service is up and running and fully configured. So hopefully that happens soon. Do we have any questions while we're waiting on our cluster to spin up and get healthy? No? Does this stuff seem possible yet? Maybe? Okay, cool. While we're waiting on those IPs, we'll continue down the road of the slides here, unless my slide software crashes. Yeah, the demo gods are not happy with me today. All right. So we didn't quite get to we did it yet, but we will very soon. And I just want to throw out some takeaways, which is that training models is actually pretty hard, pretty complicated. You need to know some things about math. You need to know some things about data science. Some more things than I know today. So if you're interested in that stuff, there are some online courses you can take. Some of them are free. There are some books that you can read. There's a course documentation for TensorFlow itself, which is pretty nice as well. But that's a whole area of expertise aside from this. The serving the models is kind of easy to do, which is nice. And GCP, gRPC, and protobuf have some steep learning curves in terms of the way that you interact with TensorFlow serving. Once you learn that stuff, it's pretty powerful. But in the meantime, client libraries are challenging and quite important. So there are client libraries in Python and Java, Ruby, JavaScript, a bunch of other languages as well. I would try to lean on those very heavily if you want to go directly with gRPC. That is something to know if you're going to use TensorFlow serving to expose these things. There's a similar tutorial for TensorFlow serving. It doesn't get into the client and the deployment of a sort of full back-end, front-end microservices model, but it is available to you if you want to try some of this stuff on your own. You can also DM me or email me if you want access to the code I'm still figuring out how that works inside of Google, but if you do message me, then I know to put you on a list for when I can easily make that available. So that's another thing. Unfortunately, external IP addresses are a little harder to come by than I was hoping for, so I'm not sure when that will come up. One more thing, if you want to try more machine learning, TensorFlow has a great website. There's also an open source tool from Amazon called MixNet or MXNet, which you can use as well, which is another machine learning environment. Google Cloud has a bunch of machine learning APIs that you can interact with, and if you just want to play around with them, for instance, the Vision API, you can actually just upload an image and then get a whole bunch of data about it, and it provides a lot more than the Inception v3 does as well, so that's also nice to know. Finally, we can be friends online or in real life. The beers are about real life. And since my external IP didn't come up in time, if you want to see this thing actually work, you want to see what kind of classifications we get, I'll just be out in the hall, and we can totally huddle around and check that out. I can tell you as an advanced piece of information, I did run the congressional building through, and it classified it as, among other things, a palace and a mosque, so that was pretty cool. And when I ran my own image through, it first classified it as a t-shirt and then classified it as a crayfish, so that was a little disheartening. But I point that out to say that the level that your trained models are accurate have a lot to do with the training that you do and the algorithms you choose and how you configure them. So again, that's why machine learning is hard. It takes a lot of iterations. That's why time is a big factor. So that's just something to point out there when you're trying to implement this stuff in real life. So I appreciate your time and attention. As I said, I'm going to wait for an IP address in the hall, and then if you want to see this stuff, come at me, and I'd be happy to show you. Thank you so much.